The purpose of this tutorial is to help you understand how to use simultaneous method to compute multiple regression. This is from Chapter 6 in the SPSS for Intermediate Statistics text, pages 111 through 124. The research question is, how well does the combination of motivation, competence, pleasure, grades in high school, father's education, mother's education, and gender predict math achievement? In order to calculate this, we will run a bivariate correlation. Scroll down to correlate, select bivariate. From here is where you will select your variables and move them over to the variables box. We'll start by pulling the first one, which is motivation scale. You can single click and move it with the arrow, and then you will put in the competence scale. Another way of moving it is just to simply double click on the variable. It moves it over to the variable box as well. And then you will put in the others, which is the pleasure scale, grades in high school, father's education, and gender. And that is all of those. We will go to our options now. And in the missing values, we want to exclude cases listwise, continue, and then we can click OK. This is going to give us our correlation matrix. Mine might look a little different than yours because I have it set up as already to show my outputs in an APA style. So this is what your output should look like. The first set of data we will look at from the analysis is the correlation matrix. The correlation matrix indicates large correlations between motivation and competence, as seen here. It also shows a large correlation between mother's education and father's education. High correlations among predictors indicate that it's likely that there will be a problem with multicollinearity. If predictor variables are highly correlated and conceptually related to one another, we would usually aggregate them or combine them, not only to reduce the likelihood of multicollinearity, but also to reduce the number of predictors, which typically increases power. If predictor variables are highly correlated, but conceptually are very different, then it may not be a good idea to put them together or to combine them. It just wouldn't be appropriate. We might decide to eliminate the less important predictor before running the regression. However, if we have reasons for wanting to include both variables as separate predictors, we should run collinearity diagnostics to see if collinearity actually is a problem. The next set of data is collinearity a problem? The video will show you how to run a linear regression with the data for this problem. To determine if there is actually a problem with collinearity, we are going to run a linear regression analysis. In order to do that, we will slide back up to the Analyze tab, drop down, and we will select Regression and Linear. This brings open the linear regression window. Our dependent variable is going to be math achievement test, because that is what we want to see the impact on. If any of these other variables impact math achievement. So we will select our independent variables. Those are motivation scale, competence scale, pleasure scale, grades in high school, father's education, mother's education, gender, and once we have entered all of our independent variables, we will double check to be sure that in the method tab it is enter, and that is already there, so that's correct. I'm going to look at the statistics tab, and we want to make sure under regression coefficients that we have estimates. We want to also look at the model fit, make sure that is clicked, descriptives, part and partial correlations, and collinearity diagnostics. That's all we will need to click from this window, so we will continue and click OK. And this is our regression data. Here are a few more outputs from this analysis. If you'll notice, it shows that the method is enter, which means that all of the variables were entered equally, that they were all combined simultaneously. The model summary table shows that the multiple correlation coefficient R, using all the predictors simultaneously, is 0.65, and the R squared is 0.43, and the adjusted R squared is 0.36, as you can see is highlighted, meaning that 36% of the variance in math achievement can be predicted from gender, competence, etc. Note that the adjusted R squared is lower than the unadjusted R squared. This is in part related to the number of variables in the equation. The adjustment is also affected by the magnitude of the effect and the sample size. Because so many independent variables were used, especially given difficulties with collinearity, a reduction in the number of variables might help us find an equation that explains more of the variance in the dependent variable. It is helpful to use the concept of parsimony with multiple regression and use the smallest number of predictors needed. The ANOVA table shows that F equals 6.47 and is significant. This indicates that the combination of the predictors significantly predict math achievement. One of the most important tables is the coefficients table. It provides the standardized beta coefficients, which are interpreted similarly to correlation coefficients or factor weights. The t-value and the sig opposite each independent variable indicates whether that variable is significantly contributing to the equation for predicting math achievement from the whole set of predictors. Thus, high school grades and gender in this example are the only variables that are significantly adding anything to the prediction when the other 5 variables are also entered. It is important to note that all the variables are being considered together when these values are computed. Therefore, if you delete one of the predictors that is not significant, it can affect the size of the betas and levels of significance for other predictors. This is particularly true if high collinearity exists. Another important aspect of the coefficients table are the correlations, 0, order, bivariate, partial, and part. The partial correlation values, when they are squared, give us an indication of the amount of unique variance that is not explained by any of the other variables in the outcome variable math achievement predicted by each independent variable. In the output, we can see that competence explains the least amount of unique variance. It only accounts for actually less than 1%, and grades in high school explains the most at 21%. Moreover, as the tolerances in the coefficients table suggest, and as we will see in problem 6.2, the standardized beta results are somewhat misleading. Although the two parent education measures were significantly correlated with math achievement, they did not contribute to the multiple regression predicting math achievement. What has happened here is that these two measures were also highly correlated with each other, and multiple regression eliminates all overlap between predictors. Thus, neither father's education nor mother's education had much to contribute when the other was also used as a predictor. Note that the tolerance for each of these variables is less than 0.64, indicating that too much multicollinearity overlap between the predictors exists. One way to handle multicollinearity is to combine variables that are highly related if that makes conceptual sense, as we previously mentioned. For example, you could make a new variable called parents' education, as we will for problem 6.2. Tolerance is also low for competence if motivation and pleasure are also entered. We will discuss what to do with these in 6.2. Collinearity diagnostics is the table that you see now. This table gives you more information about collinearity in the model. Eigenvalues should be close to 1. Variance proportions should be high for just one variable on each dimension. And condition indices should be under 15. Usually 15 to 30 is considered to indicate possible collinearity. Over 30 indicates problematic collinearity. Low eigenvalues and high condition indexes can indicate collinearity difficulties, particularly when more than one variable has a large variance proportion for that dimension. In this example, none of the condition indexes is extremely high, but dimensions 4 through 8 have low eigenvalues. Dimensions 6 through 8 have somewhat high condition indexes, and both father's education and mother's education primarily are explained by the same dimension. All of these suggest possible collinearity issues. You've reached the end of problem 6.1. The next video will show problem 6.2 for simultaneous regression correcting multicollinearity.